Hello, let me introduce myself. My name is Abimelech Garcia Aguilar, a 5th semester nanotechnology engineering student. Below I will talk to you about the work entitled, Extraction and Characterization of Biofilms, from the mesocarp watermelon, Citrullus lanatus. The issue caused by single-use plastics worsens over time. In 2018, global plastic production reached 359 million tons, a weight similar to that of the world population. Miranda, 2023. In 2021, 139 million metric tons of single-use plastic waste were generated. Whiteman, 2023. After a stagnation in 2020 due to the COVID-19 pandemic, global plastic production increased to 390.7 million tons in 2021. Of the total plastics produced in 2021, 90.2% came from fossil sources. Garcia, 2023. In Mexico, during 2022, an apparent consumption of 5.9 million tons and a production of 3.8 million tons were recorded. According to data from the National Association of Plastics Industries, ASI, ANAPAC. On the other hand, Salvador, 2023, points out that only about 3% is recycled. The Ministry of Energy, Natural Resources, and Environmental Protection, Sernapum, reported that in Tabasco, over 2,437 tons of urban solid waste are generated daily, of which 330 tons are plastics. Of this total, more than 100 tons of waste are generated in just 6 neighborhoods in the municipality of Centro, Mayalan, 2018. Due to the above, it is necessary to seek alternatives to the use of non-biodegradable single-use plastics in the region. One of the many alternatives to address this issue is the production of bioplastics from natural polymers found in agro-industrial waste. Bioplastics have been developed from cellulose, lignin, and starch. Among the waste generated in Tabasco, watermelon rind is often discarded because its various properties and components are not well known, resulting in limited research. This work aims to contribute to reducing environmental pollution caused by single-use plastics while adding value to watermelon rind, Citrullus lanatus. Therefore, its objective is to utilize the epicarp and mesocarp of the watermelon by producing bioplastics. The methodology to be employed is as follows. First, the epicarp and mesocarp are separated from the endocarp. Then, the epicarp and mesocarp are dried, and once dry, they are ground to produce watermelon flour, which is characterized for the extraction of solubles. 100 g of flour were sieved, and the material retained between 40 and 60 mesh screens was used to determine its composition. The content of extractables with organic solvents was determined in a soak-slit apparatus, according to the TAPI standard T20 for CM07. 2 grams of flour were placed in a cartridge. The test was performed in triplicate. The cartridges were placed in the soak-slit chamber, and extraction was carried out using a benzene ethanol solution. 2:1. The process was repeated using 95% ethanol. The solvents were evaporated using a rotary evaporator, 50 degrees C, and 80 rounds per minute for benzene ethanol, 70 degrees C and 80 rounds per minute for ethanol. The solids obtained were placed in a vial, and dried using a nitrogen flow until a constant weight was achieved. For the extraction with water, the method described in TAPI standard T207 CM99 was used. The contents of the cartridges were emptied into a beaker with 900 milliliters of distilled water, and heated to boiling for 1 hour. The solids were allowed to settle, the water was decanted, and the extraction process was repeated in duplicate. The remaining solid was dried by passing a stream of nitrogen. The extraction of lignin was carried out with the extractive-free material as follows. 1 gram of extractive-free material was weighed and subjected to acid hydrolysis using 15 milliliters of 72% sulfuric acid, W, in duplicate. The samples were kept under agitation at 15 degrees C for 2 hours. The suspension was then diluted with water and heated to boiling. For the extraction of starch from the mesocarp, the rind, epicarp and mesocarp, was separated from the pulp or endocarp. The epicarp was removed from the rind, and the mesocarp was washed with plenty of water, until it became clear. The mesocarp was then crushed, filtered to remove the solids, and the filtrate was placed in a beaker. The liquid was refrigerated at 4 degrees Celsius for 72 hours until the solids precipitated. The supernatant was decanted, and the sediment was centrifuged at 2,700 revolutions per minute for 15 minutes, after which it was characterized. The material retained on the filter was used for the bioplastics. 5 grams of ground mesocarp were dissolved in distilled water under constant temperature and agitation, then poured into a Petri dish and left to dry, after which it was characterized. Figure 1 shows the morphology of the flour. where flakes can be observed. This is due to the grinding and dehydration methods applied to the rind. In Figure D, a possible starch granule can be seen. In Figure 2, the X-ray diffractograms of the flower are shown. Two peaks can be observed, a broad one around 2 theta equals 18 and a more pronounced peak at 2 theta equals 21 along with another peak at 2 theta equals 34. These peaks are characteristic of the A-type pattern and are attributed to the amylose and amylopectin content in the flower. Figure 3 shows the optical microscopy micrographs of the starch obtained from the watermelon mesocarp. A large number of transparent particles with a spherical or slightly oval shape can be observed, with an average size of 5 microns. Figure 4 displays the FR spectrum of the extractives. In addition to the intense signal due to O groups, broad bands are present in some absorption regions observed in the FR spectra of the extractives with organic solvents, such as in the 1200-1000 centimeters region, where CO vibrations are observed. In the infrared spectrum of lignin, Figure 3D, a broad band of O groups from the phenylpropane structure that makes up lignin can be seen. The presence of phenol groups is confirmed by peaks at 1050 centimeters corresponding to the CO bond vibration. Peaks due to ester groups and acid groups, C equals O bonds, are also observed, along with the CO-C bond vibration from methoxyl groups. A table with extraction indices is provided next to the figure. Figure 6 shows the FR spectra of the film from the extract obtained using the attenuated total reflectance, ATR, technique. Bands with better resolution in the CO bond region, 1150-1000 centimeters, are observed, possibly due to the effect of the plasticizer, glycerol, which allows for greater separation between the chains of the components present. Figure 7 presents the TGA and DTGA thermograms of the flower, as well as those of the extractives and lignin obtained from the flower. 3 weight loss zones can be observed in the TGA thermograms of the flower and the extract, the first from 50 to 125 degrees C, corresponding to the moisture loss of the samples, where 79%, Table 4, of the mass is lost. The second range is in the 170-350 degrees C zone, with a weight loss of 50% for the flower and 60% for the extract. In the DTGA curves, peaks at 314 degrees C for the flower and 335 degrees C for the extract can be seen. The last zone starts at 350 degrees C, with the mass loss almost proportional to the temperature increase, resulting in a residual mass of around 20%. Lignin also shows 3 decomposition zones, the first associated with water loss, while the second, 175-450 degrees C, and third zones, 450-700 degrees C, with a weight loss of 84%, are associated with the thermal decomposition and carbonization of the lignin. As a conclusion, the inherent qualities of watermelon peel make it an excellent candidate for producing biofilms from the mesocarp, especially when a plasticizer like glycerol is added, enhancing its value. Other potential applications include extracting the starch from the mesocarp, or producing flour from both the epicarp and mesocarp, which exhibits diffraction patterns closely resembling those of cereal flour. Acknowledgement. Garcia Aguilar extends their gratitude to the Universidad Juárez Autónoma de Tabasco, División Académica Multidisciplinaria de Jalpa de Méndez, and the Centro de Investigación Científica de Yucatán, AC, for their support with the methodology and characterization of the materials.